Hello everyone. Welcome to this chapter on separation process selection. In this chapter, we will look at why separation is important and what are some of the key factors that we consider when we are selecting a separation technology. We will talk in detail about distillation column sequencing and what are the considerations for selection there. And finally, very briefly, we will talk about some of the hybrid reaction separation systems and just a couple of examples of that technology. So previously we talked about hierarchy of process synthesis and design, and we said that we start our process or our design process by defining the reactor specifications. For example, the path of reaction, the type of reactor or the technology of that we want to use for reaction, and other conditions, for example, temperature, pressure, conversion, and selectivity. Because once we set these parameters, they are going to affect the composition of the reactor effluent. And once we know about reactor effluent, what kind of products and compositions are in reactor effluent, we can actually start looking at how to treat that effluent or how to separate that effluent into desired and non-desired components, and also recycling of unreacted feed, for example. So today we will talk about some general considerations when selecting a separation process, and we will mainly focus on distillation process, that is a common technology, separation technology that is used in industry. This first section look at separation technology selection. So let's look at it. So as you might know already that mixing is easy and separation is difficult, because when we are talking about separation, we need to add energy because we have to overcome the entropy of the system. Okay. And when we are talking about separation, there are two factors that we normally talk about. One is how fast the separation can happen, and that is the rate of separation. And second thing is that how far we can achieve the separation between two components or multiple components, and that is what we call equilibrium. Okay. So one of the easiest separations to do is when we create multiple phases or different phases. For example, it is very easy to separate a solid from a liquid, a gas from a liquid as well. Okay, so if you have two different phases, it is very easy to separate them based on their based on the gravity. Okay. Similarly, you can have separation of two liquids from vapor, or let's say you have liquid and vapor, so like you have oil, water, and air, so you can easily separate them based on their gravity as well. In addition to using different phases, we can also use energy separating agent or mass separating agent to create these phases. For example, energy is very easy to understand, like you heat something and then you create a different phase. In terms of mass separating agent, you might want to think about liquid extraction or solvent extraction, where actually at third phase actually take selectively one of the original two phases, and then you can separate between the two original phases. Um, so it means that for separation, not only that we need energy, we also need equipment, okay, for separation. So both of these factors imply cost. It means that the choice of technology and the choice of operating conditions both can influence how much cost you are going to incur in your separation technology. So I hope that you realize here that the separation doesn't happen spontaneously. It takes time, but we can accelerate the separation process by exploiting property difference between species. Okay. And what kind of properties we are talking about here? So we can have molecular properties or thermodynamic and transport properties. In terms of molecular properties, we can look at molecular mass or the shape of the molecule or its electric charge. In terms of thermodynamic properties that we are more familiar with, we can have difference in vapor pressure or difference in solubility between different phases. We can have adsorptivity in different solid absorbents, or we can have diffusivity. It means that how fast the molecules travel, for example, in a fluid. So now if we create a second phase, that means that we will have a heterogeneous mixture that is somewhat easier to separate compared to homogeneous mixture where we only have one phase. Okay, and that is why often we try to create a second phase, and we can do that in different ways. For example, if we have a solution, we can heat the solution and evaporate some part of the liquid like solvent, or we can use an additional solvent that can selectively dissolve one of the components, for example, what we have in solvent extraction. We can also have separation by, for example, removing the vapor. Okay, so if you have a vapor mixture, we can perform a partial condensation. So it means that we will have some part in vapor, but the other part will be in liquid phase. Or we can use a liquid to actually selectively dissolve a component of a mixture like we have in case of absorption. Um, but let's say if you have a situation where you cannot create a second phase, then we have to look for some technologies where actually we can restrict the movement of one component compared to the others. Like for example, we have a membrane or adsorbent where we actually selectively separate one component from other based on their barrier properties. Okay, or we can have even more fancy techniques like electrostatic separation or magnetic separation, where we use different types of force fields to perform the separation. So here is a graphical summary of what I said on the previous slide. So we can have technologies where we can, for example, add something else to create a second phase, or we can have a barrier that can actually separate between different phases. And like for example a membrane, but strictly speaking these are not phases, but I'm just using the same language as my sources. Okay, these are uh, single phase, but it means that you have one component here and second component that is separated in the permeate and also in the retentate. And then you can have for example, instead of a barrier you can have a solid agent, like you have an adsorbents, okay, like charcoal or carbon that can absorb some components selectively while other can pass. Or we can have force fields like magnetic field or electric field, depending on what kind of composition of your feed is, and then you can separate them based on their charges and magnetism. There are several technologies for separation, and some of these technologies might be familiar to you already. Like you have flash drum, you have distillation column, absorption, evaporation, and leaching. And each of these technologies exploits one or more relevant driving forces or force fields. For example, components with different relative volatility will have different tendencies to migrate into the vapor phase or remain into the liquid phase. And flash separation can exploit these volatility differences. Um, Flash unit also can make use of gravitational force fields, for example, that can facilitate the separation of heavier liquid component to the lighter or less dense vapor component. Okay, so what are other driving forces that we can exploit? So we have, for example, here is a list of different driving forces. So you have solubility, diffusivity, uh, polarizability, van der Waals volume forces. So some of these driving forces are not familiar to me, and I guess some of them might not be familiar to you as well. So that is not important. The important point is that um, if you want to separate certain component, you need to identify differences in their properties, okay, and then find out which technologies can exploit those property differences in the best way, and then we select that separation technology. So in addition to exploiting driving forces, we can also use force fields to amplify the driving forces. Okay, for example, we can use gravity or centrifugal forces. We can amplify the differences in density. Okay, and we can also use affinity between different components with absorbent, for example, to enhance the absorption process or adsorption process. We can also use electric fields to help separate materials that are charged and from the materials that are non-charged. And one example of this separation is, for example, removal of fine particles from combustion gases, okay, that we very often using in chemical industry. So here we have some examples of which separation technologies exploit which driving forces. Okay, so you should be familiar with how differences in volatility are exploited in vapor liquid and gas liquid separations, like in distillation and flash and evaporation as well. Then we have other examples, like for example membranes, where the diffusivity of different molecules or how fast they travel inside a membrane can be exploited for separation. Differences in particle size can be exploited by using physical separation techniques like screens or filters, like a coffee filter even, for example. And then you can have same separation principle at a very much smaller scale for catalysts and adsorbents, where you have the same working principle of a filter, but now you have the molecules that are in the size of few nanometers, okay? But it's still a screening process. Some of the properties that might be less familiar to you are maybe in the last three, for example, rows here. And you don't need to worry about these properties and technologies for the purpose of the exam. The main point here, or the reason to show you here, is that we need to find the exploitable differences and in properties, and then try to match them with a suitable technology to achieve our desired separation. Okay, so we need to know what are the properties of material that we want to separate, and then what are the technologies that actually can exploit those property differences in the best way. So some of the key points in this section are summarized here. Separation technologies exploit property differences, therefore we need data to be able to select separation technologies. As such, it is really important to have a good property data model. We also discussed that separations often need energy or mass separation agents or special materials such as membranes or adsorbents. And of course, all these incur cost and may have negative impact on safety and environment. So we do need to consider all these factors when we are selecting a separation technology. Also, the majority of the cost of a chemical process or a chemical plant comes from its separation section. For example, you have the capital cost of these units because you need to build them, but at the same time, you have to operate them with all this heating and cooling requirements. So as such, we need to find energy efficient designs, and we need to perform heat integration to bring the energy cost down.